So this is my video showing you stuff about forces because there's a lot of prac stuff that we can't do since we're not at school. And then I think when we get back to school, we'll be limited in prac stuff again. So I want to show you gravity, magnetism, and maybe that'll be all we can get through today. We'll do another one for contact forces. So I have a lot of fun stuff for magnetism. We'll do that one first. I have here a bunch of different magnets. Okay, a lot of these are super magnets. Some of them are weaker. These ones are the powerful neodymium magnets. Okay, so we've got magnets, and a magnet puts out a magnetic field force. Okay, field forces are non-contact, which means my objects don't have to touch my magnet for the magnet to actually act on them. So this is how, if we have, for example, I've got these safety pins, you can see they are not touching, but then these move to actually touch the magnet. Okay, that's the idea of a field force and having a force field. The same with gravity, even though they're not close, they do act over a distance. This is pretty cool. This is some slime that I've got, but it has iron filings in it. And the iron filings then basically make the goo magnetic. So if I do this and hold it, you'll start to see it moving towards there. It's a bit slow. I'll put up a bit closer.
I can see it already.
Yeah, so it moves itself. And not just down, but it will also move it up a bit and joins together. So it kind of gets sucked up and in. If I have this down on the, I'll put it down for a sec. The other thing it will do, you see my bench, oops, lots of magnets. Watch your fingers with magnets. Okay, so it will eat it. Maybe I need a little one.
Really strong.
Yeah, oh, sorry, I pushed it. But if I put it a bit closer, it just jumps in. Sorry, here. To a point where it just jumps in and gets eaten. So yeah, that's again showing the magnetic field. But you know, what does a magnetic field even look like? So this is where we get things like this in.
Really
I love this. This is a magnetic timer. It came up. And basically it's just got really small iron filings. Now iron is one of the metals that we have that are magnetic. We're going to look at whether all metals are magnetic in a little bit. But basically all those little pieces move through there. So each of them will individually be attracted to the field, which is where we bring this. And this is a magnet at the base. Now it's not attracted to the glass, but watch what happens when I let the iron filings attach themselves. You can see the spikes there against my thing. Okay, so this is all, each of those are pointing out from the field. So at the end of a magnet, the two poles is where the strongest pull is. And then, yeah, so you can see it. And then at the sides, they're actually perpendicular, it's like sideways. So you can actually see this is what a field would look like. It starts off, let's put it in front of my coat. It starts off as pointy at the end, but then at the side, it's like horizontal, it kind of curves around. Let's try it with a different magnet. Okay. Now, so if I do this way, sideways, and let it fall on, you can see again, there's that spike, those spikes forming. And if I turn it sideways, which it doesn't want to do, you'll see they turn and they curve over sideways, okay? And then, seriously, getting focus on this is just a little bit challenging. And then if I do the other side, it goes pointy, side of it's curved, end of it's pointy. So that shows you like the, all the way around what the poles, what the field looks like. So we can actually see what a force field of magnetism looks like. It's the same for all magnets, including the Earth, has actually magnetic field that it puts out, which is protecting us against particles from the sun that are harmful, which is one awesome thing. And we think it's got to do with the movement of our outer core, which is iron and nickel, two metals that are magnetic. Okay, so that makes our magnetic field, and that is what also this is what also causes the auroras, the ions from the atmosphere, those really beautiful color rainbows in the sky at the North and South poles, because of the magnetic field and the particles being sort of vortexed into that. Okay, so that's a magnetic field. Awesome things to do with magnetism is you can have things levitate. So I have this from one of the science museums, and oh yeah, so the
I've seen things meditate before.
Yeah,
I've seen things float before.
exactly. Well, this is actually a theory we do use in a maglev train they're developing. I think Tokyo, Japan.
Japan or Tokyo.
Yeah.
One of those two are trying to make a flight.
The way this is, there's a magnet in the base here, and there's a magnet in this. And there's actually there's the two different poles. So if I balance that there, you'll actually see that it is suspended in the air. If I turn it this way, you can still see it. That's just stopping it shifting. That bit of glass there is just stopping it to shift forward. Because if it isn't there, what it will do is it will go and align up with the forces in there. Okay, so it'll line up the poles. So what we've actually learned how to do is, by keeping the poles separate and moving them, and also it works really well if you're moving it, is we can actually levitate things. And this actually reduces, one way of reducing friction, which is quite energy draining. That's friction's one of our contact forces. I'm just going to turn off my lights here. I needed it before, but I think it's see if that gives better light, better ability to see. Okay, so there we have, yes, and it's
falling. It keeps falling.
And look, if you look at that with our magnets, what happens if you break a magnet? You just make multiple magnets. So if I break this, the North and South poles now, they are, you'll notice actually that the ones that stick together, they won't, that sticks there, it won't join up with the other end. It repels. It's very strong.
Yeah, it pushes. It pushes.
It pushes it. It's called repel. And you'll notice it kind of slides it around the side. So it does that instead. Same thing, won't push the other way. So even if I break it there and try it, or break it in the middle here and try it. I know these are multiple magnets, but they line up to make one big magnet. Okay, so you can get a force, you can get movement happening within using different magnets. And we can actually make magnets from certain materials that can become magnetic. And so we can look at that. I think the next thing is, though, we need to look at what is magnetic, what makes something magnetic, or what materials are. So I have all my magnets here, but what I also have are things, and we have to figure out, are they magnetic or not? So I've got a spoon, I got some aluminium foil, I have some plastic coated paper clips, but they're still the same underneath, some bulldog clips, I have some gold rings. I also have, this is gold as well, but I have a silver ring here. I'll show you, these are all different metals. Where's the best camera point for it? Okay, so with different metals, I have copper wire and I have safety pins. Now, if I'm lucky, I have a big one. I have some safety pins. Good, I have little safety pins that are kind of the yellowy, goldy colored. And I have safety pins that are silver colored or gray. And they're actually often, not always, made of different things. They're made of different metals. This is me showing you. Okay. This is all stuff I have around home. I do like collecting things. Okay, so, and then we have the regular pins. I'll take some of these. Here we go. So a lot of people would say if something's magnetic, metals are. Okay, a lot of people have that concept. So what we're looking at is that true? Because a lot of the things around us are made of one type of metal. So we already know if I have a plastic ruler, not affected by magnets. Piece of plastic, not affected. Paper, not affected here. Cardboard, okay? No problem. But let's look at some of the other metals. So paper clips, yeah, they are. And even though the plastic, which isn't magnetic, is coating it, it still has an effect because it works over a distance. So it doesn't have to be contact, okay? Which is why you should never swallow more than one magnet or don't swallow any magnets. But the problem is swallowing multiples more than anything is because they do this in your body and they break up your inner body systems. They put holes everywhere. So yeah, don't ever swallow magnets. They're not worth it. Okay, so if I get my bulldog clip, yep, that one does it. My spoon, yep. My safety pins. Okay, so let's try. Oh, what's that there? Even, wow. Because I've got so many of them, it's quite strong, can hold up my pliers that I was using. Okay, so they're all magnetic. Let's try the copper wire. Okay, if it was magnetic, it should stay there, but it's not. Magnetic stays there. How about these safety pins? These are little goldy ones. Nope, not. Okay, aluminium, magnetic? No, not magnetic. So there's already some metals here that aren't magnetic, whatever these are made of. Let's try our aluminium. If I try my gold rings, even though they're not pure gold, so they are gold alloys, they may have other metals in it, usually copper or silver, to make them that bit tougher so they don't bend out of shape too easily. Silver ring, I know it's a silver ring because of the black on it, so it needs a bit of a clean. Nope, not that one. Gold ring, another gold ring, definitely. So gold and silver, they don't, what do you call it? They don't, and copper wire and aluminium, those metals aren't magnetic, okay? We found pretty much the things that were magnetic there. So one more thing, and I've seen this in ads for, not ads, in these TikToks and other videos, people are like, oh, you get your vaccination, it makes you magnetic, and they're like, stick a coin on their shoulder and look at, it's magnetic. I got it in my arm, so why is my head magnetic? So don't ever trust everything you see online. The other thing is, if I get my magnet, very strong magnet, why doesn't my coin stick? Stuck to my head, didn't stick to this. So coins are not magnetic. Nothing in the coins are the magnetic metals. Okay, the only metals that we have really that are magnetic, there's some rare earth metals like neodymium, which is in here. Nickel can be, and iron is the most common. And that is why all these things are magnetic. This, the back of that, these, all these things, it's everywhere, man. There we go. Okay, everything that's magnetic here, oh, that's not magnetic. Okay, everything that's magnetic that attracts to these magnets is made of steel. Okay, steel's an alloy of iron, where we put a bit of carbon in there just to make it a bit harder, so it's harder to, like, it doesn't bend as easily. Okay, so depending how much carbon, and so it's still magnetic. Okay, so that's magnetic materials. Pretty much most of the things are all steel things. If it's not made of steel, if it's made of aluminium, if it's made of gold, copper, these are copper and nickel. So even the nickel in there is not magnetic. These things aren't magnetic. Okay, so now we know magnetic materials, pretty much just iron in everyday things, and mostly because it's steel. So some things you can do with magnets and magnetism is you can magnetize these things if they're made of iron. You can do it with a nail. And what I'm going to do is get myself a needle or a pin. Here's a needle. And this is one that you can often see online, how to make a compass. Okay.
Oh, I've seen that video. I've seen a video of that.
Yeah. So what you do is you basically, annoying sometimes. Wow, look at that. Okay, so you stroke this. If you tap the magnet or bang it too much, you actually lose its bit of its magnetism, because inside, basically, if you think about it, there's all these tiny little things we call domains that all line up in one direction. When they line up in one direction, they make it into a magnet. Okay, so there's one end that's like the North Pole, one that's the South Pole. So there's a very distinct difference. Okay, so yeah, but if you drop them, you start to knock those out of position. So even though things are made of metal, they can be still delicate. So we stroke our pin here. We're going to make this into a compass. What we're doing is we're getting all the domains in there lined up in the same direction. And what I'm going to do is grab myself a cup and stick this on. I'm going to touch it with my fingers so it gets a bit oily, and that should help it float on the water. Yeah, new cup. Okay, so I've got my water. Let's turn this down a little bit so we can see, and I'll see if this will float. Look, it does not float. Let's
You need a piece of paper to make it float properly.
Yeah, I need a piece of paper. Let's find some paper. All right. Piece of paper. Cool. Get another needle. Oh, actually, there's a way that you can make that paper float in the middle. Let me make that happen. Right. If you fill your glass in so the water's kind of up over the top, it'll float right in the middle. That is a neat trick. Now, where's the magnet here? Okay, so I got my other needle. Stroke it, same direction. And then lay it on top here. And now you'll notice it turns on its own accord. And so it's going to be pointing north and south, or it's actually going to be pointing probably towards these which are closer. So you'll notice I can move it around depending on the magnet, because they're strong magnets, they're working quite well. So if I bring this end, oops.
You made it
I saw that. It went over in the middle. Okay, so if I do that way, so I'll do it at the front. You can see. Whoops. All right, so turn it that way. You can see it's pointing there. Try again. Nope. Oh no, did I drop it into? Third needle's a charm. What I want to show you is watch what happens when I change the pole in here. So stroke it. Lay it down. Okay, so I bring this into the magnet near, but if I swap it over, look what happens. It turns it around. This is actually one of the theories in making motors work, is that there is magnets continually spinning around and turning the center. So if I keep doing this, I'll keep turning it, and that's kind of the basis for a motor, interestingly. Okay, spinning it round and round. Anyway, so yeah, that's how compasses work. And if there was no other magnetic interference, it should point north and south, and you could figure that out. So towards my computer is south, and towards me is north in my area here. So you can kind of see it. It's aligning this way. So that's south is kind of that way, north is that way. All right, so making. So we've done a few cool things here with magnets, but I also wanted to show you a bit of gravity stuff. I watched a really cool video the other day, last night actually, I found, about gravity and an astrophysicist explaining it to an 8-year-old, a teenager, and a college student, a graduate student, and an expert in the field. They're having really big discussions on what gravity is. And the thing she told the 8-year-old, I think, is what's really useful for us. So we're going to grab a few balls and have a look at gravity. I'll move out the breakable things out of the way. Okay, so I have a few different balls here. They all have different masses, okay? And people often say heavier things fall faster. That's generally what people think, because we think that, it's heavier, it's gonna hit the ground faster. So what I wanted to set up is a way of checking if that's actually the case. So what we're gonna do is, I've got some, I've got some clay. If I had plasticine, that would also work, but I don't have plasticine and I have clay. So what I'm going to do is put some clay out between some bit of baking paper, and then I'm going to drop the balls on it. We'll have a look at whether they hit at the same time. So we're going to have a look at that. And we're also going to then have a look at, do they hit the ground at the same force? Okay, because the force of gravity is the same on us on Earth. Gravity is the force between two objects or two bodies, they often say. Now, we actually pull on the Earth because we're a body and the Earth is a body. Body is something that has mass. But, the Earth's a lot bigger. So if there was a tug of war between us and the Earth wins, which is why Earth pulls us back down when we move up in the air. It pulls towards the center. Okay, let's grab a bit of this out. Oh, okay. Now, to make this a bit even, I'm just going to spread this all out on my bench, and then I'm going to roll it out with a rolling pin. But because I've got my rolling pin having the stuff on it, I'm also going to cover my rolling pin with some of that paper. Can't get this out. Ooh. Things to remember to set up beforehand next time, guys. All right. So that baking paper, because I don't really want everything getting, so this is what I've done. I've put some of this down, using some baking paper, and I'm going to roll it, flatten it out. Okay, what we're going to do, this will be able to show how much force the ball's hitting the ground here with. Okay, so I just wanted it to be like that to roll it, avoid getting so much mess on the bench. Okay, so I'm going to then drop 2 balls at the same time from the same height. So I've got high bounce balls, and I've got a ping pong ball. Okay, so what I'm going to do is I'm going to drop them from the same height, which is why I have the measuring tape. You could do this at home if you wanted. I picked the balls because they're actually the same size, or pretty much the same size. So let's get a meter. Meter's always good. A nice standard unit. 80, 90, 100. Okay, so I'm holding this 1 meter above. I want you guys to notice, I'm going to just let them drop, let them fall with the force of gravity from the same height at the same time. Okay, we didn't actually see when they hit, so let me do this again. What you might have noticed is that's where the heavier ball hit, that's where the other one hit. So I might roll that smooth again and do it one more time. See if it happens the same every time. Try and roll it. Okay, so yeah, hold it up at 1 meter. Move this back a little bit, or not. There we go. So we should be able to see when they both land and if they land at the same time. So let's do this one. Holding it at 1 meter. Oops. 3, 2, 1. There we go. So when did they hit? They hit at the same time. Even though this one is heavier, it's denser, it's got all the plastic in it, the ping pong ball actually landed at the same time. And the other thing, maybe you can see, depends on the quality. I'll lift it up to show you, is where they hit. Now I need the lights back on. Where they hit, there's a bigger dent where the heavier ball hit, and there's a smaller dent, which is that one's there, not this one. That's my finger. Or is it that one? No, that one. Yeah, they're right next to each other. That one is a smaller dent made by the ping pong ball. What that shows us is even though they fall at the same speed, due to the force of gravity, they hit the ground with different force. Heavier objects hit the ground with greater force than lighter objects. That's what the difference is. So that's a cool experiment to practice and look at about physics and about gravity. With that, that's also why adults, when we fall off, you know, rides and other kids' things, we injure ourselves a whole lot more than the kids do because we're bigger, we're heavier. And especially if we're not small, we also falling a greater distance. So there's more force in that involved. So the force of gravity in today's lesson, the second lesson about contact forces, gives the force of weight. Weight, it says gravity, but it's really the force due to gravity of an object. So our weight is how much our bodies, our mass, pushes down on a surface due to the force of gravity. Engineers need to know this because when they're designing buildings, they need to know exactly the forces that are going to be involved so that they're able to calculate that things are going to be able to be built without falling apart. Okay, so the way that we actually figure this out, we know the force of gravity, and there are experiments you can do to show what the force of gravity is, the speed of gravity, so speed of acceleration. That's a bit more complex, so we won't do that now. But what we want to show you is that on other places, other planets, that objects will have different weights, even though they've got the same mass. So for example, my bouncy ball here with my kitchen scale, ta-da. If I weigh it, we say weigh too, because we're actually getting our weight, subtracting the force of gravity on it, and finding our mass. So this weighs 53 grams, and this one weighs 2 grams. Okay, so 53 to 51 grams heavier. And that's why we saw that bigger dent with it. Okay, so on Earth, the force that this pushes down onto the surface is 53 times roughly about 10, okay? So 53, I think it was kilograms. So 53 grams, 0.05 kilograms, times that by 10. So 0.5 newtons would be the force that this pushes down on the ground with. This one would be a lot smaller. I'd have to do the math, and I don't think you need to worry about the math for it. But the idea is that on Earth, the force due to gravity basically multiplies your mass in kilograms by 10, and you get the force that you're putting down on the ground underneath you. Okay, but if you're on the moon, it's different. And if you're also in the 0G space, so that's where you're orbiting the Earth and you're actually constantly falling. That's why they say 0G. You don't have that gravitation, you don't feel it, but you're constantly, the whole ship is basically falling back to Earth, but luckily at the same time it falls back to Earth, it's also going around the Earth. So it's kind of spinning around, stops that from happening, stops it from being crashing to the ground. It's acceleration around. So in that case, things act differently too. And that's why I've got some activities to show you next lesson on toys in space. It was really interesting. I was watching just some of the basic toys they had and how it acted in space. Okay, on the moon's gravity is 1/6 of what we have here. Okay, so basically it wouldn't be, so things don't fall with the same speed and they don't hit the ground with the same force, they don't have the same weight because the force of gravity is different. If you have a look at people spacewalking, moonwalking, not like the dance steps, actually on the moon, you'll notice they kind of do these little hops and stuff and they kind of float in the air a little bit. They don't like drift off into space, but like, even though their packs are heavy, they actually, they have to work really hard to go across rather than up too much. I have video, but I don't know where it's gone, of me in a space chair to show that. So that's the other thing about gravity. Different planets, the gravity pull is different. And we know from the video I'll show you, the moon has a gravitational effect on the Earth, and so does the sun. And that's what happens with our tides. The Earth also pulls on the moon because the moon's close. And even though it's smaller than the sun, it's closer, so it has a greater impact. So gravity is dependent on how heavy the body is, its mass, but also how close it is. The sun's heaps bigger, but it's further away than the moon. So they kind of almost have a similar sort of pull effect, especially when they're multiplied together. And when we learn about tides, and I don't remember where we do, but when we learn about tides, we look at how where the moon and the sun is changes our high and low tides that we have. So that's gravity, okay? 2 non-contact field forces. And I'll do another lesson, maybe tomorrow, on looking at contact forces, in particular friction and buoyancy, because they're the 2 ones our program gives us a little bit more activities on.